There is a column of gas and dust 6,000 light-years from Earth that looks in visible light like a hand reaching out of a cloud. We have been staring at it since 1995. And then, in October 2022, James Webb looked at the same patch of sky, and what it sent back was not a better version of what Hubble saw. It was a different picture entirely. The dust that had blocked Hubble's view, Webb saw straight through it, and inside that dust, protostars, jets of shocked gas, structures that had been invisible to every telescope ever pointed at this region. This is what Webb actually found, not a poster, a data set. Let's start at the beginning, with why the pillars exist at all. The pillars of creation sit inside the Eagle Nebula, Messier 16, a stellar nursery roughly 6,500 light-years away in the constellation Serpens. The nebula itself spans about 70 light-years. The pillars are a small feature, roughly 4 to 5 light-years tall. That scale is worth sitting with, 4 light-years tall, the whole distance from the Sun to Proxima Centauri stacked vertically. The pillars are made mostly of hydrogen and dust. They are what's left after massive, hot, young stars burned off everything around them except the densest pockets. Those pockets survived. They're called elephant trunks in the literature, elongated, dense molecular columns pointing toward the radiation source that shaped them. The process sculpting them has a name: photoevaporation. Ultraviolet radiation from nearby stars strips the outer layers of the pillar molecule by molecule. The result is that the pillars are simultaneously being destroyed from the outside and, possibly, building new stars on the inside. That tension, creation happening inside a structure that's being eaten alive, is exactly what Webb was designed to expose. Now, what Hubble could not see. Hubble works primarily in visible and ultraviolet light. Dust is opaque to those wavelengths, so every Hubble image of the pillars, stunning as it is, shows only the surface. The interior, everything happening in the dense gas cores, was invisible. Webb operates in near-infrared and mid-infrared, longer wavelengths. They slip through dust the way radio waves slip through walls. Webb has 2 primary instruments used on the pillars: NARCam and MIRI, near-infrared and mid-infrared. They see different things. Both matter. NARCam cuts through the outer dust and shows stars, young stars that had never been clearly resolved inside the pillars before. MIRI, the mid-infrared instrument, goes further still. It maps heat. In MIRI's view, the mature background stars almost disappear. The dust itself glows, and the structure of the gas becomes visible in a way no other instrument can achieve. Together, they tell a story that has 2 chapters: what the young stars look like and what the gas around them is doing. Along the edges of the pillars in the NIRCam image, you can see bright crimson and orange knobs, wavy, almost lava-like structures. Those are not artifacts, those are jets. When a protostar is still forming, still accreting mass from the disk of gas around it, it periodically fires jets of material outward along its poles. Those jets slam into the surrounding gas at enormous velocity. The collision is called a bow shock. Webb's NARCam captured dozens of these bow shocks across the pillars, each one a sign that a star was born there recently. In the 1995 Hubble image, those same regions looked like a flat, bright edge. Webb revealed they are a living, dynamic boundary, material actively moving, colliding, glowing. The protostars themselves are still embedded, still wrapped in cocoons of gas and dust, but Webb can detect their heat. One figure from the initial Webb data release: researchers counted over 100 newly detected young stellar objects inside and around the pillars. 100! In a region previously thought to be relatively quiet in terms of active star formation. This matters for a specific reason. The pillars have long been debated. Are they forming stars? Or are they past their prime, being eroded too fast for new stars to finish forming? Webb's protostar count is strong evidence that yes, stars are forming there right now. Not a relic, not a dying structure, a nursery still operating. And this is where the MIRI data starts doing something unusual. In mid-infrared, the pillars themselves glow. The dust is not cold, inert matter. It is warm, heated by radiation from those nearby massive stars. That surface layer, the one being actively photoevaporated, shows up in MIRI as a brighter boundary. You can trace the erosion front in real time. Think of it like watching sand erode off a cliff in slow motion. The MIRI image is the moment that erosion is happening, frozen by Webb's snapshot. One of the striking structural details in the MIRI data is the wavy, layered edge of Pillar 1, the tallest column, the one most people think of when they picture the pillars. Those waves are density variations, regions where the gas is a little more or less compressed. The radiation hits those differently, creating the ridged, almost muscular texture you see. In Hubble's view, that same edge was smooth, an artifact of limited wavelength resolution. The corrugation was always there. Hubble simply could not see it. There is something philosophically interesting happening here. The pillars look the same to our eyes in both images, but the science extracted from each is almost incomparable. Hubble gave us composition and shape, Webb gives us physics. Now, the jets. Because this is the detail in the Webb data that most researchers cited first when the images dropped. Those crimson lava-like wisps along the edges are hydrogen emission, specifically ionized hydrogen, the H-alpha signature that astronomers use to trace energetic gas. When a protostellar jet punches into the surrounding molecular gas, it excites the hydrogen atoms. They absorb energy, then release it as light. That light is what Webb detected. The important thing about detecting those jets is what they imply about the star doing the firing. Protostellar jets are only produced during a specific window in a star's formation, the early accretion phase. If you see a jet, you know the star is young, very young, still feeding. Some of the jets Webb detected extend for several tenths of a light year. That is enormous, longer than the distance from the Sun to its nearest neighboring stars, just in the jet alone. And Webb found multiple jets firing in different directions from different embedded sources throughout the pillar structure. This is not one star forming. This is a community of young stellar objects, all in different stages, all interacting with the same gas column. The question researchers are now working through: are those jets affecting each other? Is the turbulence from one protostar's outflow triggering or disrupting collapse in the gas nearby? That question, feedback within the stellar nursery itself, was essentially impossible to study before Webb gave us this level of resolution at these wavelengths. Let's talk about what the MIRI image revealed about the thermal structure, because this is a detail that did not make most of the press releases. In the MIRI image, the background field, the space between pillars, is almost completely dark. Not because it's empty, because mid-infrared light from cold, diffuse gas is very faint at this distance, but the pillar surfaces glow. And that glow is polycyclic aromatic hydrocarbons, PAHs, large carbon-based molecules on the pillar surface that light up under UV exposure. PAHs are significant. They are present in interstellar space throughout the galaxy, and some researchers believe they represent a chemical precursor class relevant to organic chemistry. Detecting their emission on the surface of an active stellar nursery in the process of being irradiated is exactly the kind of contextual chemistry data Webb was built to collect. There is a detail in the Pillar 3 region, the shortest of the three main columns, that shows a distinct dark lane cutting across its base. That dark lane is not shadow. It is an extremely dense filament of cold molecular gas, so dense it absorbs even the near-infrared light Webb uses. Regions like that, dense enough to block near-infrared, are exactly the conditions where the earliest collapse phase of star formation occurs. So even where Webb cannot fully see, the absence of light is itself the data. This is a principle that runs through all of Webb's science. Where the photons stop, you learn something. Now, an honest note on what Webb did not resolve, because precision matters here. Webb did not settle the debate about whether the pillars are net producers of stars or net consumers. Stars forming faster than the pillars are eroding, or slower. The protostar count is high, but estimating final stellar mass from this data requires spectroscopic follow-up that is still being done. What Webb confirmed firmly: stars are forming. How many will reach main sequence? That is the next question. There is also a 2007 Spitzer Space Telescope result worth knowing. Spitzer found evidence of a supernova shockwave traveling through the Eagle Nebula, one that may reach the pillars in about 1,000 years. If that shockwave hits, it would destroy the pillars in a relatively short span, on the order of tens of thousands of years after impact. This possibility reframes the whole situation. The stars forming inside may be the last generation that pillar ever produces, and we cannot see the pillars as they are today. We are seeing them as they were 6,500 years ago, the time it took for the light to reach us. There is a real possibility the pillars no longer exist in their current form. The shockwave may have already arrived. Those photons just haven't reached us yet. Webb captured something that may already be gone. That is the particular condition of observational astronomy. You are always reading old light. Let's come back to what Webb added to the wider science of star formation, not just the pillars specifically. The pillars are close enough and well studied enough that they function as a calibration benchmark. Whatever models we use to explain what Webb sees there, we can test those models against decades of prior data. That makes the pillars scientifically strategic. Webb's observations here don't just describe one nebula, they sharpen the tools we use to understand all stellar nurseries, specifically the relationship between photoevaporation timescales and star formation rates. How fast can new stars emerge before the cloud they're forming from gets eaten away? The pillars are one of the best natural laboratories to measure this because the radiation source, the geometry, and the stellar content are all relatively well constrained. Now, what did researchers actually say when the data dropped? The team noted that the new census of young stellar objects was significantly higher than previous estimates. The pillars were more active than the pre-Webb picture suggested. They also noted that the spatial distribution of those young objects was different from predictions, more concentrated near the pillar tips than the interiors. That spatial pattern points to a process called radiation-driven implosion. The idea that ultraviolet radiation doesn't just erode the pillar from the outside, it actually compresses the gas just beneath the surface, triggering collapse there first. Radiation as the trigger for the very thing it's also destroying. The irony of that mechanism is not lost on the researchers working with this data. The massive stars of M16, the ones carving the pillars, may have contributed to creating the very stars now forming inside them, stellar generations linked by light. So what will the pillars look like if the shockwave doesn't arrive in, say, 1 million years? The models suggest the pillars will thin at the top, losing mass to photoevaporation, while the lower sections, further from the radiation, erode more slowly. The stars currently forming inside will eventually clear their own cocoons, literally burning away the gas around them, and emerge as open, visible stars in the nebula field. Some of them may become stars similar to the Sun. A few may form planetary systems. The molecular material in those same pillars, carbon, oxygen, nitrogen, is the raw inventory of chemistry. The dust in the pillars of creation is not so different from the dust that collapsed to form the solar system 4.6 billion years ago. The pillars are not a curiosity. They are a mirror showing us, at a distance of 6,500 light-years, a process that happened in this solar system's past. And Webb has given us the clearest look at that mirror that has ever existed. When the 1995 Hubble image came out, it became the most reproduced astronomical photograph in history. It appeared on posters, stamps, album covers, and the walls of classrooms. The 2022 Webb image is a different thing. It is not a photograph in the traditional sense. It is a false-color scientific rendering, assembled from data taken in wavelengths invisible to human eyes. The colors you see in the JWST image, the amber, the blue, the wisps of red, are assigned by scientists to represent specific chemical and physical processes. They are a translation, a language for the invisible. What Webb captured is, in one sense, not what the pillars look like, but in a more honest sense, it is exactly what they are. Every color is a measurement. Every bright knot is a physical event. Every dark lane is a region dense enough to resist the light trying to pass through it. This is what a stellar nursery looks like from the inside. Not a painting, not a metaphor. 6,500 light-years away, gas is falling inward under its own gravity. Young stars are firing jets into the space around them. The column they live inside is being eaten by light, and we, on a small planet orbiting an unremarkable star in the outer arm of this same galaxy, have now built an instrument precise enough to see it. That fact, that we can see it, is not a small thing. If this kind of science interests you, the real data, the unresolved questions, the missions still running, this channel covers it every week. Subscribe and we'll keep going deeper.